This problem asks us to sketch the function f is x to the fourth minus 18x squared. It's going to be a great example of the way that you can combine algebra and calculus in order to understand what the shape of a function is going to be. The first thing we're going to do is locate the roots of the function, the place where the function equals 0. Then we're going to use calculus to determine where the function is increasing and decreasing. The second derivative is going to tell us where the function is concave up and where it's concave down. Having found those critical points, we want to locate their x and y coordinates so that we can locate them on the graph. And then we're almost done. We just have to combine the information that we got from all of the previous steps. You may notice that I've been giving away the answer throughout this whole discussion because up here in the upper right hand corner we have a graph of the function. I've already highlighted everything I just told you. We've got the roots, we've got where the function's decreasing and increasing, just clearly visible. You can see right here the function's concave down. We have all of those critical points located, all of it sitting right there. The point really isn't the graph at the end of the day. It's learning how to use all this sort of information that we're going to find by combining algebra and calculus to know what part of the graph we need to be focusing on to see its critical features. To find the roots of this function, we're going to first factor it, take out the common x squared that we see, and set that equal to 0. X squared minus 18 doesn't actually factor any further than that, and so we end up with x equals 0, and x equals plus or minus square root of 18, which is plus or minus 3 square roots of 2. The x equals 0 term comes from the x squared being set equal to 0, and the square roots come from saying x squared minus 18 equal to 0. To figure out where the function is increasing and where it's decreasing, we need to take the derivative. We see we can factor out of 4x. And we can keep factoring to get it all the way down to 4x times x minus 3 times x plus 3. And then to look at the critical points, we want to set that equal to 0. That gives us x is 0, positive 3, and negative 3. I find it's really a lot easier for me to keep track of where the derivative is positive and negative if I use those critical points I just found, the places where the derivative equals 0, put them onto a number line, and then figure out where the derivative is positive and negative. So, for example, if I am working over in this area where we've got numbers bigger than 3, I'll take something like a 4, plug it into the derivative. When I plug 4 into this term here, I get a positive number. I don't care what it is. When I plug a 4 into the x squared minus 9, I get a positive number. I don't care what it is. So all told, that tells me the derivative here is positive, which means the function is increasing. And I keep testing that with all of the other points, and I get this pattern that says the function's initially decreasing, then increasing, then decreasing, then increasing. Concavity is controlled by the second derivative, and to figure out where the second derivative is positive and negative, we're going to once again want critical points, this time for the second derivative, and they're at plus or minus root 3. Once again, I'm going to use a number line. This number line this time is based on the critical points for the second derivative, and I'm going to be plugging sample points back into the second derivative to figure out where it's positive and where it's negative. So for instance, a number bigger than root 3 is about 1.7, so a number bigger than root 3 would be 2. Plug a 2 into the second derivative, end up with something positive. In between the two square roots, 0 is the easiest number. I plug that in, I get a negative value. and down there it's positive, which of course means that the function is concave up when the second derivative is positive, concave down when the second derivative is negative, and concave up when the second derivative is positive. We found a bunch of critical points, places where the function equals 0, where the derivative equals 0, where the second derivative equals 0. And those are all going to be giving us interesting features of our graph. So let's call them interesting points. We want to figure out where those interesting points sit on the actual graph. And this is a mistake people will often make, in that they will plug the numbers into, say, a derivative that they'd computed, but you want to know where the point's going to sit on the graph. So we're plugging back into the actual function f. The roots are easy, that's where the function was equal to 0. If we want to figure out where the critical point corresponding to x equals minus 3 sits, we have to put the minus 3 back into the original function. We're going to end up with negative 81 when we go through that computation. When x is 0, y is 0. When x is 3, y is once again negative 81. Similarly, we're going to end up with negative 45 is the y values for the spots where the second derivative equaled 0. We finally get to use all this information to graph the function. We're going to put in the actual coordinates of the critical points, locate them here in the xy plane, and then use the information about increasing and decreasing to sketch the function. So as x heads up towards minus 3, we know that the function is decreasing. We get that from right there. We know that it's concave up. We get that from right there. And so we need something that's decreasing and concave up. Between x equals negative 3 and x equals negative root 3, we switch to being increasing, staying concave up, then increasing concave down, decreasing concave down, decreasing concave up, increasing concave up. Just for fun, let's compare a sketch I made by hand with a graph I made using Mathematica. On the left is my sketch, and you can see that it has basically all the same features as what was produced by the computer. The key issue here is I needed to tell the computer the place to look, the exact x-coordinates I wanted to make my picture, and then I chose to highlight features like this minimum value of the function. However you choose to render the graph in the end, it's the calculus and algebra that's going to tell you what are the critical features that your rendering needs to be illustrating.